Okay, sending a signal faster than the speed of light in real life. So just to jump right on in, we're not going to be talking about Cherenkov radiation or anything like that here, where yes, charged particles can go faster than light through certain mediums, most famously happening in nuclear reactors. This though is because, of course, the light has slowed down, meaning that particles going faster than it are not actually going faster than c, the speed of light in a vacuum. We are talking about sending a signal faster than the speed of light in a vacuum. This probably raises a few questions for you. Maybe you're sitting there ready to try and poke holes in the theory, so let's dive right into that. There are a few things you need to know in order to start piecing this all together. The first is that light changes speeds depending on what medium it's passing through. So for instance, a beam of light will speed up when going from water to air or from air to vacuum. There are many videos online for why this is the case, and you can do a deep dive in your own time. The shorthand version would be the more energy in the way, the slower light goes. Not the actual reason, but a nice way of thinking about it. Okay, so the second thing to note is that space is not actually empty. It is in fact full of virtual particle pairs popping into existence and annihilating themselves all the time in the blink of an eye, or even faster. These virtual particle pairs, as a result of vacuum fluctuations, the way to think about this, all the physics nowadays is pretty much dealing with fields. That's just the way it looks at everything. So you have, for instance, the electromagnetic field. It has a whole lot of wavelengths associated with it, potential wavelengths. The idea being that every potential wavelength that can exist does exist in space at all times. This means that space is an incredibly energetic area. The most dramatic, or possibly the most famous, probably both, experiment to highlight this involves getting two conductive metallic plates and placing them really close to each other. So close that it starts to cancel out the possibility of certain wavelengths between the plates. You cut out enough wavelengths, you cut out enough energy, that is, and the energy on the outside of the plates is so great compared to the energy on the inside that the plates experience a pushing force. They come together. This is what's known as the Casimir force. Quite famous, as I was saying. What's less commonly talked about, or maybe you talk about it all the time, less commonly talked about in my circles anyway, is that the elimination of virtual modes in a Casimir vacuum should also eliminate their would-be scattering, resulting in an increased speed for massless particles. So that's a very long-handed way of saying that you shoot a light beam into a Casimir vacuum, it should speed up. This is what we're going to be building our theory around. If you've got a problem, that's where you can find it. But I should point out, this is not actually my theory. It's been out there for a long time. If you hop onto Google Scholar or the like, something similar like that, and look up papers like this one is very good, Speed of Light and Non-Trivial Vacua, yeah, you can read all about it. This is from 1994, so this is not a new theory. So why am I talking about it today? Well, that's because we're going to build a setup to exploit it, or at least try to. You might be sitting there going, well, hang on, this idea is 3+ decades old now. Surely someone else has tried this before now. The short answer is no, not that I can see. And the reason for that is essentially engineering difficulties. So if you had tried building this 20 years ago, it would have been nearly impossible. You would have had to be maybe one of the richest companies on the planet and just funding it to the nth degree. Like it wasn't feasible. 10 years ago, it would have been extremely difficult. Nowadays, engineering has come so far that what was impossible maybe 10 years ago is now accessible engineering, even for your average Joe. So, to start, we're going to need two plates that are machined to incredible levels of flatness. So we're talking gauge block levels of flatness here. Very difficult thing to do. I'm based in Australia. I had a look around for a long time. I found one company currently able to get the type of precision needed. I don't know the rules for YouTubing, by the way. Even though I think this is quite a bonus, talking about this company in a positive light, I'm still not going to drop their name because I don't know how that works. Maybe it counts as advertising when I wasn't asked to, and I'll get in trouble. I don't know. There is a company, however, which was able to do what I wanted. Took a little while, but I eventually got back 2 very flat plates. Putting them to the test, because obviously you want to test these things out just to make sure there's no kinks in your plan or anything. So I did a little setup. Here are the 2 plates sandwiching a piece of Glad wrap on each side. I've got a dodgy laser pointer aimed at the gap, balanced on a deck of cards. I just removed 1 card at a time until the laser was at the right height to shine through the gap, and you can see it on the back wall there. This is not the final setup by any stretch, but it's a good idea when doing an experimental setup to start with some cheap, this is how I'm going to approach things, before jumping to the final result. So anyway, we've got the steel blocks. They seem to be great. They were just what I was after. Time for step 2. Part 2 was a lot trickier. So the whole idea of this experimental setup is to try and get a beam of light to go from one spot to another faster than C. The speed up is directly related to the amount of energy that we're removing from between the 2 plates, and this is already tiny, so it's reduced as the 4th power of the plate gap distance. Some quick back of the envelope calculations for a ballpark figure, how far apart these plates need to be, and we've reached the figure of around 100 nanometers, which is really, really small. I can't stress how small that is. So the Glad wrap in the previous example, that's way too thick. If we were to use paint or any other sort of coating, way too thick. Anyway, long story short, after a lot of looking around, I found a company in America that specializes in carbon foils used for beam targets in particle accelerators. They were very helpful. Once again, I would drop this company's name in a heartbeat if I thought I was allowed to. I don't know the rules, though. They were very friendly. They shipped me out a few of their targets. They came to around $100 a piece after shipping, and I had to buy a few of them because they don't just sell them individually. But again, they were helpful, very friendly, thumbs up. Next problem is getting the carbon foils into position. This turned out to be quite the experience. So as you can imagine, 100 nanometers thick, they're incredibly fragile. They ship them on these little glass substrates, and the way that you're meant to get them off is you're meant to submerge them very, very slowly in water. First you have to scrape the sides to make sure that they don't stick or anything like that. Then you submerge them in water exceptionally slowly, deionized water and a whole lot of other little things you need to prepare for this. But even when doing it as slowly as I could, it would still tear, it would still rip. It was never completely smooth. I was fairly happy with the results in the end, except for one little detail. So I'm showing the video now just because, well, I've got it and you might as well see what I was up to. You can see it just starting to tear here, and that'll become a lot more pronounced in a second. The tear is okay because, well, it doesn't really matter. As long as the foil makes the gap the right size, then what does it matter if there's a little bit of a rip? The problem came at the end when I place the foil on the metal plates. First off, that's rather tricky. The metal plates are extremely flat and so act as extremely hydrophobic material. So water doesn't beat up on them or anything like that. It just flows right off. And the carbon foil with it, which is a pain, but enough fiddling around and I eventually get it. The real problem was, and you'll see it, I zoom in at the end of this little video clip, the foils wrinkle up, they crinkle as they dry, and it causes folds, and these folds would take it from a very exact 100 nanometers, which is around the ballpark that we want, to, well, more than that, and hence what we don't want. So anyway, a lot of back and forth emails with the company. Again, great company, thumbs up, would recommend. And in the end, we hit on the idea that if I were to ship them the metal plates, they could deposit the carbon foil directly onto the metal plate instead of going via a substrate, then taking it off the substrate, floating it on deionized water, taking it from the water to the plate. Skip the middle step, and it should, in theory, flatten out. So this was a much pricier option, and one that I wasn't willing to invest in without having got the rest of the experiment right. But it is just a money problem. It wasn't particularly expensive, but it was more than I was willing to put in at the time. So I consider that problem solved and can go on to, well, the next part of getting this all together. So here you can see the problems, even just little waves, and the foil just floats away, which is a real pain. You can see one of my previous attempts actually on the edge of the block. I figured that's okay. This was all just a bit of a try and get the process happening, work out the kinks, etc., etc. I was recommended a couple of different techniques. The one which is failing the most here is draping. So with a surface which isn't completely hydrophobic like these are, or don't act completely hydrophobically, you're in theory meant to be able to just touch an edge of the foil to the material you want to attach it to, and then lift it up on a diagonal, and it will drape and attach as it goes down. That was not working, so in the end what I had to do was lift it up as straight as I possibly could, and as the water ran off on all sides, the foil was left in the middle and just attached. So again, quite the experience. I think I did a pretty good job considering my hands, I thought they would be shaking. Expensive material, didn't want to stuff it up. You really don't get too many shots, well, before having to reorder everything all over again. It's not like you can just peel this stuff off the plate once it's on. But yeah, one foil on one plate. I got a foil onto the second plate. The idea being that when I sandwich them together, as long as I keep those foils apart, there will be a gap between them, and that's our roughly 100 nanometer gap. Again, for the real process, I will have to go back to that company and get them to deposit the foil directly on. That also has the added bonus that they can place the foils in the exact position that I want. So in theory, if it turned out I needed a longer gap in order to measure the light speed change or something like that, I could ship them some slightly differently shaped plates, perhaps some elongated ones. They would be able to attach in the correct positions and still have a gap from one end to the other. At this stage, some of you might be going, now hang on, Casimir force experiments are notoriously difficult to set up. So even with advanced engineering options at my fingertips nowadays, because we're living in the future, how am I managing to set up a Casimir experiment in my lounge room when some labs struggle to set it up, for instance? And the answer is we have one very big advantage over every other Casimir experiment out there. We're not looking to measure the Casimir force, which pretty much all the others are. So if you want to measure the Casimir force, the general setup, I believe, is a sphere on a pendulum type setup, swinging very closely to a metal plate, and then you measure the deflection of the sphere, and it's a whole process. We don't need to do any of that. We just want the Casimir force to be there, and to do that, all we need are two metal plates sandwiching something very narrow, which is what we've done. So anyway, I just thought I'd mention that in case you were curious. Moving on, the next problem to overcome with this setup is a bit of a two-parter, and it starts with how do you measure a change in light speed? So the most high-tech, common way to do that in the modern age is with something called LiDAR, light detection and ranging, I believe it stands for, something like that. The idea being you get a light source, it shoots out into the distance, it hits an object, scatters in all directions. Some of that scattered light will come directly back to the LiDAR machine, and that will measure the time that it takes to go there and back, and from that establish a distance. So you could use this if you imagine, say, measuring the distance to a lake bed wall. You shoot it through the air, it goes, it comes back, it measures the distance, it goes, okay, it took this long, so the distance is X. If you then went back to the same lake bed when it's underwater, same position, you shot it, the light would take longer to travel to the wall and back because it's going through water, not air. The LiDAR would register that as a change in distance, and you could factor that in, figure out the numbers, all would be well. The problem comes in that, for a very good reason, almost all LiDAR is infrared. This is a safety thing. You wouldn't want, say, an automatic car driving down the street using non-infrared LiDAR because it would blind everyone that drove past, for instance. Most automatic cars use LiDAR, I believe. There's one company that doesn't. Again, I'm not naming names or anything, but LiDAR is quite common technology in the world nowadays. It comes with a problem though, in that infrared has a wavelength roughly 10 times the size of our gap. So here's a little chart straight from Wikipedia. You can see the wavelength measured in nanometers down below. Infrared is up here and way too thick. We're looking at 100 nanometers, which is in fact down this way, and we're pretty much looking in the X-ray region. So, two-part problem. The first being we need a light source with a wavelength of around 100 nanometers, which our little $20 laser that we used for the glad wrap setup at the start isn't going to cut it anymore. We pretty much need X-rays, a lot harder to work with. The second part of the problem is how do you measure a change in light speed for X-rays or the like. So I did have a look around while on the LiDAR track, seeing what other similar options were out there. It turns out there was a NASA probe that used a UV LiDAR, but I couldn't get in contact with anyone that had anything to do with it. I did reach out, but I'm guessing NASA gets swamped by these sort of questions all the time, and that's fine. There is a solution though. So while LiDAR is the modern high-tech version of measuring a change in light speed, the old school option is called a Michelson interferometer. So what this does is you take light going down two different paths, they meet at a point, they cause interference, either constructive or destructive interference, and then if one of the light sources changes the distance that it travels to reach the path, or in our case changes the speed that it travels to reach the path, that interference pattern will change subtly. And it's not as great as a LiDAR for measuring, like it's not going to give you numbers or anything. You can crunch them, I guess, but it will do the job. Michelson interferometers are designed with normal light in mind, and these vary in price from, I think a home put together one might fetch maybe $300, and they go up to maybe $2,000, but they can be modified for X-rays. So you just need something at the back which is sensitive to X-rays, and don't stick your eyeball in the way. The other problem is how do you set up the experiment using X-rays. For this, I turned to my dentist friend and asked if I could use his office space after hours, and he very nicely agreed. We encountered another problem though. So the dentist X-ray device that my friend has in his office, it's a little handheld device where you click it and it gives a short burst. And it's also, being a handheld device, not designed for sitting down on benches and staying in spots, so it's actually quite rounded. So the first part of the problem, okay, you can be very cautious and very delicately set it up and don't move it and then click the button, and that's fine. The problem comes in that it is not a continuous beam, it is a very, very short burst. So you set up the films behind the gap of the metal plates. You set up the X-ray to be roughly pointing at the gap, but it's very, very difficult, in fact almost impossible, to get it exactly pointing at the gap. So the deck of cards that I used in that first setup, that's not going to cut it anymore. And while I could do a similar setup, where you point, click, check, did the light go through, no, take away something very narrow, point, click, take it away, etc., etc. The fact that it's not an instantaneous feedback, so you can't go, oh look, I removed a card, now it's at the exact right height because the film at the back is showing me. You need to send the X-ray through and then go essentially develop the film. Like, it's not actually developing film nowadays. I don't know the actual technique behind it. I'm not the dentist, but it's time consuming anyway and not instantaneous. And the fact that I can't leave the experimental setup in his office overnight, like it's a place of work, a business, he needs access to his X-ray machine during the day, this wasn't really a viable option. So I looked around. There are really three possibilities that I chose in the end that to look into. The first was businesses out there. So there are plenty of businesses in the world with all sorts of strange equipment and setups, and they'll do odd things. And I thought, well, maybe one of them will have the equipment that I want or be set up for experiments just like this. So I reached out. Pretty much every business got back to me with the same thing, saying, no, look, that's too specialized, we can't do this, we can't do that. I did find one business in China that said, yes, we can do that, but the price that they quoted me was, I could put a down payment on a very nice house for the price of that experiment setup, so that wasn't really an option. The second option was academic institutions. So I had a look around, I messaged a lot of them. About 2/3 of them got back to me. The universities were very much, no, look, we really only want to do experiments with people that go to our university with our own students. That's what our equipment's for, not for outside experiments, and that's fine. There were a few institutions which had the equipment, but the most promising one, which I actually had some back and forth with, they were booked out for the indefinite future, essentially, years. So they had the experimental setup that they wanted for their experiments, and that equipment could be repurposed for the setup that I was looking at, but I would have to be on a waiting list for a very long time. So maybe I'll drop them a line again someday in the future, but we're looking at I don't even know, like a half decade, maybe a decade. Like they're booked out for a long time. So that was a bit of a bust. The last option, and grasping at straws here, I looked at, well, I actually follow quite a lot of engineers on YouTube. They do some amazing things, people making superconducting magnets and all sorts of stuff in their basement. I thought, well, maybe one of them would have the know-how and the willingness to collaborate and, well, see what we could get happening. Only one YouTuber got back to me. I don't know if that's a thing with YouTubers where they don't check their mail or they just dismiss any idea that's not their own. Who knows? Maybe I'll find out one day. The one that got back to me, they said, oh, look, we're busy for a while, fill out this paperwork. I did that and haven't heard back from them since. So I don't know if I got lost in their filing system, if they're really busy, or if they just weren't interested. And this brings us to where I'm up to today. So the experiment, I think, is still solid. If you've got any sort of ideas or feedback on the theory, if you think there's a problem that I've overlooked, feel free to let me know below, and I will look into it, because I've put enough time looking into this already. I feel I'm quite ready to address any problems that might crop up. If, on the other hand, you're watching this and you think, hey, hang on, I could do this, drop me a line. I would be happy to collaborate with anyone out there on getting this to happen. I want to see it happen. I think it would be great to be a part of the first signal to go faster than the speed of light in a vacuum. For those wondering, hey, hang on, why are you actually bothering? So we're looking at, depending on the gap that we make between the metal plates and the strength of the Casimir force, we might only be looking at a change of a few meters a second. So light goes at 300,000 meters a second, or give or take. So a few meters a second is not very much of a change, and you might be going, well, what's the point? But every little bit is progress, right? So not every breakthrough has to be Star Trek style, where they go from following the laws of physics to warp speed in the one movie. You can just go, well, break the limit by a few meters a second, and maybe a century from now someone else will come along with an idea going, well, we can add a few more meters a second to that, and baby steps. Apart from that though, and I'm just going to end on a little side story. So back in the day, what got me into physics, I would have been a year 7 student, so not even a teenager at the time, and I was introduced to the double slit experiment. Now, as a kid, this was like discovering real life magic. Like, it just blew me away. And to be fair, they were giving sort of kiddie explanations where if you look at what slit an electron goes through, then it changes the interference pattern. And the magic side of things was possibly hyped up. It took me many years to get to the bottom of it. One, because I was not even a teenager, and two, the internet didn't exist at that time. So it took a long time, but that was the beginning of my pathway through physics. I suggest anyone that hasn't looked into the double slit experiment to do so. This is just a picture from a wiki page. It is fairly clear nowadays. There's a bazillion videos on it if you want to check it up in your own time. It really is still a great experiment and the best introduction to physics. But the reason that I bring this up is in my mind, the adult equivalent of the double slit experiment is the delayed choice quantum eraser experiment. This is much less well known. It's still fairly well known in the scheme of experiments in physics, but it's much less well known than the double slit experiment. This one blew me away all over again as an adult, and the reason is that it is so elegant the way that nature enforces the speed limit c upon the universe. So you've probably heard before that quantum entanglement allows instantaneous affecting of you affect this atom spin over on this side of the universe, and an atom with spin on that side of the universe is decided. Media and sci-fi and stuff nowadays tend to blow it out of all proportion, which is a shame because the actual mechanics of what's happening are so again, I'm going to use the word elegant. So what's happening with the delayed choice quantum eraser experiment is you have streams of entangled photons, referred to as signal and idler streams, with the aim that what happened to the idler photons would influence whether the signal photon stream displayed an interference pattern or not in the past. So it's a delayed choice because the photons are entangled, but one of those streams is delayed while the other one you're reading the answer for, getting the results. And while technically it's successful in that, yes, the interference pattern is either there or not with no regard to distance or if the signal photons are already observed, there's always two patterns at the end, at the signal photon end. And when the interference patterns are present, these perfectly overlap in such a way that an observer can't immediately distinguish the result from there being no interference pattern. The only way to see if a pattern occurred would be to compare the coincidence counts. Essentially, you need to send another stream of data from the idler stream. Essentially, you need the idler stream, which is the slow one, as a kind of a decoder wheel, I guess you could say. And that idler stream has to travel along regular channels, so essentially limited by light speed. So while you can argue that, hey, wow, the first photon was decided whether or not it would be interfered with or not based on the second photon's actions later in time, you can never actually get to that information until the time has elapsed for regular information channels. Anyway, I possibly went into a little bit too much detail there. Sorry about that. That is my favourite experiment. I feel it's okay to get a little bit carried away with it. But the reason that I brought it up is because I think it would be quite fascinating to combine what we're going for in this video, which is signalling faster than C, with the delayed choice quantum eraser experiment and try and get information out of the overlapping interference patterns earlier than, well, otherwise we're limited by. So essentially testing whether information is actually limited by the speed c, or so does something in nature pop up and reinforce that like it did with the overlapping interference patterns, or is that just a quirk and we can get around it with essentially faster speeds? I think the speed of information is bound to the speed of light. That's an interesting question. Okay, and one last thing, because I realise some people out there will be going, now hang on, doesn't this conflict with special relativity if you can send signals faster than light? Actually, the answer is technically no. So as long as you can't establish a fixed simultaneity relation between two separated points in space-time, everything's fine. That is, you can't imply a preferred inertial frame using faster than light signaling. A nice easy way to understand this, for those that don't like the jargon, is if you were to look at Stargate, they have a portal where they step through it and they take pretty much a slide through the universe at high speed and come out another portal. That's fine, but the Rick and Morty type portal, where you step through and you're instantaneously on the other side, like you can have one leg in one world and one leg in the other, that's not fine, according to theoretical sci-fi. So anyway, as long as you can't have a preferred inertial frame, special relativity stays intact. And I think that's everything. So thank you for watching. If you've got any comments or any questions, feel free to leave them below, and I promise to get back to you before too long. Otherwise, I hope you enjoyed it, and feel free to leave me your thoughts. See ya.